Okay guys, in this video segment we're going to talk about thermochemical equations and how we actually can use a little stoichiometry to solve for energy change when we run an actual chemical reaction. Okay, so first thing, what is a thermochemical equation? When you deal with thermochemical, we're breaking it down into two pieces. Thermal means there's thermodynamic data there, or there's numerical values for energy, and of course the chemical part is just a normal chemical equation. A couple of things you need to keep in mind as we do these thermochemical equations is that you need to have your physical states present and you need to be under standard conditions. So we don't really vary off of the 1 atmosphere of pressure or 25 degrees Celsius when we do these process or these equations. If we take a look, here are two different thermochemical equations and they're similar, but we see some obvious differences in them. Both of them are a normal chemical equation, two different types of reactions here. The first one's written where you get the thermodynamic data written in the end, and the other one's written so you have your thermodynamic data written first. Okay. What I'd like you to do when you read these equations is don't treat these numbers as anything special. What I mean by that is this reaction has a mole ratio of 1 mole of this to 2 moles of this to 1 to 2 to 890. What we're saying is for every 1 mole of this we react, we're going to make 890 kilojoules of energy. For every 2 moles of water that we make, we're going to make 890 kilojoules of energy. So basically, this 890 can become part of a mole ratio in a stoichiometry problem. On the same token, we had the same idea here, but here we put it on the left-hand side of our arrow. And we do that to represent something different. So if we look, if we're producing, on the right-hand side of our arrow, if we're producing energy, versus the left-hand side, we're absorbing or reacting energy. That tells us something different about if the energy is being released or if the energy is being absorbed. So in this case, energy is being released, so this is an exothermic process. In this case, the energy is being absorbed, so that's an endothermic process. It really is no different than in previous units where we just put the triangle, but now we're starting to quantify it or put numbers to that. One thing you need to make note of, when we use these numbers in our mathematical calculations, you might see them written like this also, where they just say the heat of the reaction is a negative 890 kilojoules. Notice how we don't put the negative up here because it's assumed when you write it on the right-hand side of the arrow. Where on this one, we end up with a positive 242 because it's on the left-hand side of the arrow. Okay? So anytime you pull a number out of this equation that's on the right-hand side of the arrow, you have to tag it or mark it with the negative sign to represent energy being released in that process. Okay? Now, when we deal with these heats of a reaction, or when we deal with these reactions either giving off energy or absorbing energy, which kind of relate back to our previous video segment, we also can write them as separate values. So we don't have to write a thermochemical equation. What we can do is write a normal chemical equation and put the thermodynamic data below it or next to it or someplace in line with it. So in that case, we would put the negative sign in and we would not put the negative sign in if it was absorbing energy. Okay? So in these cases, when we write them separately, if we take a look, the one in red is going to be exothermic because we're releasing this much energy. The one in blue would be endothermic because we're absorbing that much energy. Okay? If I ask you to put this number in the equation, you'd put this one on the right-hand side, you'd put this one on the left-hand side. Okay? Now, taking this idea of a reaction that has thermodynamic data in it, we actually can solve some changes in terms of the energy. Along with that, we can actually do the same process for solutions. Okay? So one of the things that sometimes students struggle with is this idea that when you generate a solution or you dissolve something in water, that can't change energy, but actually it can. And we actually utilize that stuff for our chemical hot packs. If we take a look, as we dissolve calcium chloride, we actually can make calcium ions and chlorine ions in solution. We talked about that in our previous unit also. If we dissolve ammonium nitrate, we make ammonium ions and nitrate ions in solution. This process, even though it's not chemical, it is a physical change, does release or absorb energy. So in the case of a hot pack, because this process is exothermic, it's releasing energy, that gets to release out as kinetic energy, and it will heat up the water that's in that solution, so then we will see that temperature rise. In this case, the water that's in this solution will get cooled down because it's pulling energy from that water, which is our endothermic process. Okay, so just like heats of a reaction where we have energy change, when we do a heat of solution, it's identical in terms of what's going on in terms of the math. It's just that we're making a solution instead of a chemical reaction. So you can apply the same concept over two different scenarios. We tag it with an S, that just stands for heat of solution. It allows us to identify that we're not really doing a chemical reaction here, we're just creating a solution here. Okay? Now, a little side note, if you're wondering about the hand warmers, those disposable ones you buy before football games, hockey games, that kind of stuff, those are usually oxidation of iron, so there is no solution there. What they do is you break them open, squish them around, and then the iron starts to oxidize in there, which is also exothermic. And if you ever dealt with self-heating meals, it's exactly the same process. They just use more of it, and they use magnesium, which generates a more exothermic process than the iron would. So it's the same concept, but applied a little differently for your self-heating meals, as if you ever use those in either backpacking trips or if you have a relation to a military family that may have had some exposure to those different things that are there. Okay. What we want to do now is take this concept and then apply it to some stoichiometry. Okay. So what we can do is we actually can calculate what is our energy changes within a reaction if we know how much of the substances we're using. So here's our relationship. We have 2 moles of magnesium with 1 mole of oxygen making 2 moles of magnesium oxide, and we're releasing 1,204 kilojoules of energy. So if I'm going to react 454 grams of magnesium, how much energy is actually going to be released here? Okay, we know that 2 moles of magnesium gives us 1,204, but 454 is not 2 moles, so we have to be able to put that into our stoichiometry and solve for that. Okay, so we'll go to the board and we'll work this guy out. So I have 454 grams of magnesium, and I want to figure out how much energy is being released here. Well, I know magnesium has a molar mass of 24.31 grams per mole. And according to my balanced equation, I'm using 2 moles of magnesium. That's the coefficient from the equation. And I produce 1,204 kilojoules of energy. Now, because, if you go back to the screen, because we have this written on the right-hand side of our reaction, this number has to be made negative because it's being produced or it's exothermic. So I'm going to put a negative sign in there, and then I have my setup. Okay. The hardest thing for students is realizing that this relationship exists. That if you know your moles of the reaction and you know the energy from the reaction, you can set them equal to each other on a conversion factor. Magnesium cancels. We solve for kilojoules. So now we just take the 454 divided by 24.31 times a negative 1,204, and don't forget to divide by 2. If we do that, we end up with 11,200 kilojoules of energy, and that is the energy change for this reaction. Now keep in mind that if I gave you a starting value in energy, you could also solve for how many grams of magnesium you used. So really think about energy not as a separate thing here, but as just another piece of the puzzle in a stoichiometry problem. So if I give you energy, you should be able to solve for any of your substances. If I give you a substance in grams or liters or volume or mass, you should be able to solve for energy, and vice versa. If we take a look at our second practice problem, this one says, what volume of H2 gas can I make from electrolysis of water if I use 2.437 kilojoules of energy at 25 degrees Celsius and 99.9 kilopascals of pressure? Okay, so this problem has a little twist to it because we're looking for a volume of gas, and we're not at STP, so we need to apply the ideal gas law here to get us some information and then be able to use the stoichiometry also. Okay, so we know the energy. So what we want to do is let's figure out how many moles of hydrogen we're going to make. And once we know a mole of hydrogen, we can use the ideal gas law to solve this. Okay? So the problem gives us 2.437 2.437 kilojoules of energy. And we know from our balanced equation that it's 241.8 kilojoules of energy for every 2 moles of hydrogen that we produce. And that's going to give us an answer in moles. And then, once we know our answer in moles, we can apply the ideal gas law and solve for our volume. So we can say that volume is equal to our number of moles times R times T divided by the pressure. But we need our number of moles from here to insert into the equation there. Okay? So if we do that, we can go back to the screen here, and we see that we take our 2.4 times 2.437, convert to moles. Knowing the ideal gas law, we can rearrange that. We now insert our moles here, not rounding that number off. We know R. We know our temperature, which is the 25 degrees plus the 273 to get to Kelvin, and our pressure was 99.9 kilopascals, and we can solve for a volume of a half liter of volume here. Okay. Be prepared to use the ideal gas law as a tool within stoichiometry problems. You might know the volume and have to solve for moles and then do stoichiometry. Or you might know the moles and have to solve for volume using the ideal gas law. So be prepared to use it as a tool within these type of problems. It is part of this unit and being able to do that. Okay. There's additional practice for this on worksheet number 2. So please go ahead and take a look at that, and then we'll also do some additional practice in class. Thank you.